All right, this is Dr. Sheldon Drobot. I'm the Mission Area Lead for Environmental Intelligence and Sustainability at Ball Aerospace. It's time to welcome everyone to our first InterMET.digital webinar of the new year. And that gives me the opportunity to wish you all the very best for 2022. Let's hope it's a good one. We certainly know we need it. So this latest webinar forms episode 2 of our climate change special report on the opportunities for addressing the causes and impacts of climate change. Well, on episode 1, we looked at the business opportunities associated with technologies used for detecting and monitoring climate change. Our focus this time is more specific on measuring, monitoring, and modeling water and air quality. Our 4 panelists will be looking at the current state of the science and how the private sector is working to solve part of the problem. So joining me today are Dr. Oksana Tarasova, head of the Atmospheric Environment Research Division of the Science and Innovations Department of the World Meteorological Organization. We also have Phil Father, the CEO of Scepter, Incorporated, Dr. Walt Meyer, Senior Research Scientist at the National Snow and Ice Data Center at the University of Colorado, and Aravind Ravichandran, the Director of Strategy for Space. So, welcome again to the audience, and I would ask, as the speakers are giving their presentations, we have a little Q&A button at the bottom, and that is your opportunity to put in questions for the speakers. Note that we'll go through all the presentations first, and then we'll get to the Q&A. So let's get right to it, and let me introduce you to Dr. Oksana Tarasova. So Oksana is the head of the WMO's Atmospheric Environment Research Division for Science and Innovations Department, and she started at the WMO in 2009. She has a background in physics and a PhD in atmospheric physics. Previously, she worked in the Lomonosov Moscow State University and at the Max Planck Institute for Chemistry in Germany. At the WMO, she has led the Global Atmosphere Watch program since 2014. She's also served as a president of the Atmospheric Sciences Division of the European Geoscience Union, co-chairs the task force on measurements and modeling of the LRTAP convention, and is a member of multiple international projects advisory boards. Very impressive, Oksana. The floor is yours.
Thank you very much for introduction, and let me just jump in on the topic. Let us just start. So I will be talking about the role of WMO in air quality agenda, as you outlined in the topic of this webinar. And first of all, I just wanted to bring to your attention why at all we are looking at air quality or atmospheric pollution. There are several points which I want to make here, and the first is that outdoor and indoor air pollution is considered as one of the key risk factors for health. There are 7 million premature deaths which are associated every year with the indoor and outdoor air pollution. There's also millions of US dollars which are lost due to reduced coral production around the world due to deposition of tropospheric ozone, which is one of the major pollutants. Also, the deposition of nitrogen causes some problem for our biodiversity and ecosystem in multiple countries. At the same time, air pollution is also interlinked with climate. Air pollutants are climate forces with the tropospheric ozone and its precursors, providing about plus half degree of warming since pre-industrial time, and the cooling impact of about the same magnitude of half degree due to the aerosol and their precursors. So there's multiple reasons why we want to look at the air quality. And of course, when we look at air quality, to understand what happens around the world, we need to make measurements and we need to see what is happening on the ground. And for that purpose, the World Meteorological Organization 30 years ago established the Global Atmosphere Watch program, which I'm leading in WMO. And this program provides the international leadership in research and capacity development in atmospheric composition, observation, and analysis. And we do it through the long-term systematic observation of atmospheric composition with a particular focus on quality assurance and quality control and creation of the integrated products and services that are relevant to the users. And why we do it based in the international organization, it was clear from the beginning that what we wanted to understand are the physical and chemical changes in the atmosphere rather than the differences in measurement techniques between different countries. So that's why, to understand the physical processes and geographical distribution of air pollution, we need to use the same units on the same scale all around the globe so we can put all the data together and understand the processes that drive the pollution. And WMO is a leadership organization that provides the standards, international standards, in atmospheric composition observation and modeling, and also we advise member countries on the best way to implement these standards. On the map on the right, you can see the GO station information system. This is where we collect the metadata about the stations which are performing the measurements under our program. And you will see that the map is not uniform. There are some regions of the world where you have substantial gaps, and the other parts of the world are pretty well covered with these observations. So there are challenges in implementing the system. You see there are geographical gaps. There is also gaps in the vertical distribution because there's not many profiles which are measured. We also have differences in the parameter coverage. There are many more sites which measure CO2 than the sites which measure volatile organic compounds due to complexity of these measurements. Also, we have some issues, or let's say challenges, implementing this standardization because in different countries, buying the calibration cylinders can be quite challenging to ensure the quality of the observations. And also we have a difference in policies because in some countries, air pollution data are not encouraged for the open sharing, while in the other parts of the world, this is openly available. There are many observations which are done still in research mode, so if we wanted to move it from the research mode to operation and make them relevant to policy, policies in some countries related to data sharing must be reconsidered. The ways to fill in the special gaps in observations are done by innovative techniques like the implementation of the low-cost sensors or use of satellite. And we've seen those efforts are growing. And we saw that there's quite a lot of low-cost sensors which has been implemented all around the globe. And in WMO, we performed an assessment of those measurement technology and provided the guidance. The last guidance has been produced just in the beginning of last year when we published the recommendation. And what we also noticed that there are plenty of different agencies and players who try to implement the measurements of atmospheric composition. It's not that they are not all using the same measurement technique, but they are not even talking to each other. So sometimes the same country receives different channels, multiple pieces of equipment, which cannot even talk to each other. So there is a lack of coordination. Concerning the low-cost sensors and how they compare with the regulatory scale equipment and the satellite measurements, both have the advantages and disadvantages. When we speak about low-cost sensors, probably their cost is their advantage, but there is a substantial lack of evaluation of this measurement technique. There is plenty of interferences. When you use this measurement technique, it says that it measures NOx, it measures also PM, and the worst, it measures also water vapor in the atmosphere. So you actually cannot clean up the signal which comes from the sensor. There is no standardization on the sensor setting, so people put it in different places, which gives a different representation. And if you put the network of the sensor, they create a whole bunch of data which you need to put are specially distributed and get the analysis of this data. So when we work with the data coming from the sensors, we need to be extremely careful what actually it means. The satellite data, on the other hand, absolutely brilliant if you want to have the global coverage, but they don't measure what we are interested in. The satellite measurements are indirect. The satellites measures the irradiance on the top of the atmosphere, and then you have to put a very complicated atmospheric model to retrieve the parameter which you are interested in. There is a confusion in the community that the total column measurements, like all the gas which you have in the atmosphere, can be easily converted into concentration by just multiplying it by a particular coefficient. That doesn't take into consideration any mixing, any atmospheric dynamics or anything. We've seen this approach in health community, and this is wrong. So when we produce the data, as you can see, there's a lot of different ways to produce the data. What do we do with them? Within the GOLD program, we have 7 dedicated data centers where the data from the stations, so GOLD stations, are submitted, and they are openly available. We try to improve the timeliness of the data when they are delivered, but at the current stage, the delivery is within 1 year since the measurements has been performed to ensure the quality control of those data. And as part of the community which we are working with is a research community, we are also broadly endorsing the fair data sharing principles. What is extremely important is that when we see that the data are openly available, many people, even within our research community, consider that this is a free cheese. So they go download the data and they publish the papers or produce added value products. This leads to the cut of the funding to the people who actually produce the data because attribution was missing. So the stakeholders were confused that these are the people who use the data, are the producers of the data. So I think that it's extremely important that when we speak about the open data policy and open data sharing, especially for the public good purposes, attribution is key if we wanted to ensure the sustainability of the network. Also, we need to be aware that when we start sharing the data, there is a, let's say, there is a whole a pyramid of what is available and what is the open data means. Because there's plenty of observations which exist, somebody does the measurement, probably the data can be partly accessible if you can get a negotiation and get some particular pieces of data. But for the data to be programmatically available, we need to ensure that there is an interface that can allow the machine-machine interaction between the data repository and the data user. And the data, to be useful, have to have additional information about what it is, additional set of metadata that describe where the data was collected, what is their quality. Only the observations that have the appropriate interface and the appropriate metadata can be considered useful for the user community, because only then the user can understand what is the quality and what they are dealing with. Then it comes to the modeling. So we also combine the observations with the modeling through different techniques like the measurement model fusion or data assimilation, and we produce a lot of the forecasts. We've done the survey within the community, how many centers are participating in the production of the forecasts. There are at least 55 centers that are global, regional, or national in nature, and I think there are many more, so we just did not reach broad enough to the community. The issue with the air quality forecasting is that each model produces its own forecast. And unlike the weather, in weather, we have a very good system for scoring of the model performance. Such scoring for the model performance for chemistry transport models is not developed yet. The only evaluation mechanism which we have now is the multi-model comparison, where we can establish a degree of equivalence between different models. And it is recommended that then the public products are produced. We strongly recommend the multi-model average or the ensemble average for the different forecasting products. You can see the sun and dust storm forecasting system, which is developed by our regional North Africa and European node in Barcelona Supercomputer Center. And you can see that there are 12 models which are participating, and if you look at the same score on the map, 12 different models will give you 12 different answers. The users can be confused if they take only one or if they take two. So we strongly recommend the multi-model forecast. I also noticed, and working in WMO, that when we communicate about air pollution, there is a tendency to oversimplify the thing. People think that pollution is the emissions and there is nothing in between. So it's quite an easy topic. In reality, air pollution is quite a complicated topic, which includes atmospheric dynamics, vertical transport, horizontal transport. It includes chemistry. It includes interaction with biosphere, with the ocean, exchange processes. To understand how your observation and analysis can drive the policy, you have to actually understand the complexity of the system and communicate together with your data the interpretation, what it actually means. And I'm just basing it on the experience which we had during the COVID, when people started looking at the NO2 signal from satellite and said, okay, so this is a decrease in NO2 column, so that's proportional to the emission reduction, and this is the surface concentration as well. Well, that's not correct. About 30%, or in some cases, the different percentage of the signal was actually related to the change in metrology rather than emissions. So to do the attribution of what happens on the political scale, on the emission control, and what happens with the observing the atmosphere, it's extremely important to communicate all this chain and what is in between and what it actually means. With that, I thank you very much.
All right. Thanks very much, Oksana. We'll be returning to some of those great points you've raised later on. But now let me introduce you to Philip Father. Phil is a serial entrepreneur who's launched businesses in high-tech satellite communications and renewable energy. Among his recent endeavors, Philip founded Trio Renewable Gas, which specializes in the deployment of modular thermochemical conversion equipment to generate renewable energy and sequester carbon. Definitely a great effort. And now this effort was done in partnership with Fortune 500 company SAIC. Prior to Trio, Philip co-founded Protostar Limited, a satellite communications company that provided direct-to-home television services across Asia using several high-powered geostationary satellites, which the company financed, built, and launched. Philip's now running Scepter Incorporated, an integrated data analytics company whose mission is to provide comprehensive atmospheric information on a global real-time basis. So Philip, take it away.
So as a follow-up, we put Scepter together to really understand what's going on in the atmosphere. So I'm glad that Oksana was able to lead here and explain all the complexity of monitoring the atmosphere. Our mission here is really to try and render the atmosphere's dynamic composition on a global real-time basis. And getting to those attributes opens up a bunch of commercial markets for us. So think about us as sitting at the center of big data, Earth observation, and ESG. So again, following on the back of Oksana, it's a dynamic, complicated interaction. And in order to understand basically what you're seeing there in the second graphic at the center of the page, we're launching our own hyperspectral sensors to capture the missing characteristics of elevation and other attributes. And as I'll show you, we use terrestrial sensors and other sensors in the column to really understand that transport layer and everything that's going on in the atmosphere. And our whole thesis here, borrowing from Drucker, if you can't measure it, you can't improve it. So when we set out years ago to really hone and understand our approach, we realized that given the dynamic composition, the more sensors, the better. We're sort of the guys, though, bringing in two key aspects. One is our own space-based hyperspectral sensors, but we grab other sensors in what we call the vertical air column. So that could be terrestrial in situ sensors, drones, aircraft, stratospheric platforms. And we integrate and normalize all of those sensors in a fusion platform. And then we can move forward with that and fuse with other data sets. So think of such things as wind, if you're interested in methane and methane dispersion. It could be epidemiological records, if you're interested in health effects, et cetera. And then there's some amount of analytics and machine learning that's then presented into that process. And then we get into a visualization step. And so through that, we actually transform the data into actionable atmospheric information, or think about us as providing comprehensive situational awareness. And we patented that. So those patents have been accepted in the US, Europe, and China. So in order to do this mission, think about us, since we're commercially oriented, as providing a multi-sensor payload. So I think this is an aspect that makes us unique. We're not looking at one vertical. We take a cross-industry approach. So we take a look at shortwave, visible, near infrared, midwave, particularly for wildfire detection, long wave for evening missions, and even some fluorescence capability. And then we add these sensors on as the markets develop. And then we have one platform here that can see the entire atmosphere. So I mentioned earlier on that it's one thing to grab the sensors, but you have to data fuse. So we have a highly scalable architecture to do that. And so we can take our own customers' sensors. These could be methane sensors. They could be in situ air quality sensors, as I mentioned before. And we can protect and keep the data secure but we can also normalize and data fuse with other data sets and turn it around and make a higher level product for our customer. So when you take a step back and think about, well, what could you do with atmospheric information? Well, with atmospheric information, I'd encourage you to think about the following. On a corollary, you can think about how many markets now that surface imagery serves. So that would be the digital globes and the planets out there. But we're looking at the data cube that sits on top of that surface imagery. So there's all sorts of use cases that I could give you for revenue enhancement or cost savings. Also strategic decision making. So for instance, how does the Port of Long Beach and its activity affect the health of citizens in Riverside County, at 2 o'clock in the afternoon? The big market that we think for us is really being driven by ESG, because many Fortune 500 companies now are mandated through the capital markets to understand what their input and imprint is on the atmosphere. But what's missing there is the data set. Also, there's use cases in defense, and obviously with air quality management districts, we can actually help add the three-dimensional view to their in situ terrestrial sensors. So recently, while we have a broad mission, we recently announced going deep, if you will, in one industry vertical, and that's in the energy industry. So just in December, we announced a big partnership with Exxonmobil, in which we're going to use our broader platform to drill deep on doing methane detection. And we're unique here in that we're going beyond just simply detecting or quantifying. And then as we move from quantify, we're going to go into informing the company, moving into abatement procedures, and then ultimately certifying that the leak has been fixed. So this is how you could imagine one moving from just simply detecting with the data set, but putting together a compelling information service offering that's pushed to people out in the field. And then finally, how do we do all of this? We do it with an ecosystem of partners. We're not vertically integrated on our technology stack. So we don't follow the model where we build our own bus, build our own sensor, that type of thing to save cost. We believe that the costs have come down significantly, let's say because of innovations in the new space economy, where we partner with best-in-class providers like Ball, AER, and others to build our tech force. We integrate it. And in this case, we get best in class at let's say COTS, and we're much more comfortable then of mission success. So we do this through an ecosystem of partners. And I think that's it. Thank you for your time.
Okay, great, Phil. That's excellent. I'm sure we'll get lots of questions from our audience. But now let me introduce everyone to Dr. Walt Meyer. So Walt's the Senior Research Scientist at the National Snow and Ice Data Center, also known as NSIDC, and that's within the Cooperative Institute for Research in the Environmental Sciences at the University of Colorado in Boulder. So Walt serves as a lead scientist for NASA Snow and Ice Data Center, and his research focuses on remote sensing of sea ice and polar climate change. Walt, over to you.
All right, thank you, Sheldon, for that great introduction. So I'm gonna talk, I'm gonna show a little bit different. I'm gonna show you some data from of sea ice. Sea ice is the ice floating in the ocean, grows and melts within the ocean. And it's one of the areas that we've seen big changes as the climate has changed. It's been one of the early and most dramatic indicators of climate change. And as Sheldon mentioned, I'm at the National Snow and Ice Data Center. We're part of the Cooperative Institute for Research in Environmental Sciences at the University of Colorado. And I'll just mention, we have several scientists that research cryospheric and data science, and we manage and distribute a significant amount of data, particularly from NASA. We're a NASA data center. And so we provide much of the NASA data of the snow and ice covered regions. And all that data is available for free. It's public and open access data. Jumping in here to what we're seeing in the changes. Oops, I skipped a slide. As I mentioned, sea ice is an area that we're really seeing big changes in the Arctic. This is just 2 maps. This is in September on the left, showing when we reach generally the minimum extent, the lowest extent of the year. And then in March on the right, when we reach our maximum. So the ice grows and melts seasonally, it melts back during the summer, and grows outward during the winter. And what you see with the blue is indicating a significant downward trend in ice, where ice is lost as much as 20% lower concentration in the summer and September. And in the winter, it doesn't look quite as dramatic, but still, as you look in the kind of the outward southern areas, there's the blue is quite evident there, losses of ice. And I'll mention these are data from passive microwave sensors on NOAA and US Department of Defense satellites. So these are obtaining data in the microwave range, emitted energy in the microwave range. There is a data gap near the pole due to the orbit configuration and the sensor characteristics. We don't get data right near the pole. But we can get significant data around that shows really strong trends. And if we look at the total area covered, what we call extent, which is area above a concentration threshold of 15%, again, you see this very significant downward trend here, particularly in the summertime. There's variability from year to year. It goes up and down, but overall, there's a strong and strongly statistically significant, greater than 99% confidence level, downward trend since our data starts in 1979. In September, 80,000 square kilometers per year, or close to 13% per decade. That's the loss. That's equivalent to a loss of about 1 United Kingdom or 1 Colorado every 3 years or so. And overall, we're down over 3 million square kilometers in terms of the total area loss, in terms of the linear change. And that's about twice the size of the state of Alaska. In March, winter, it's not as dramatic. It still gets dark and cold in the winter. The ice still grows outward. But again, we are losing ice at about half the rate, and the percentages are smaller because the overall extent is larger. But both of these show significant declines in the Arctic extent. And to show it even more dramatically, I have this animation. This is looking at what we call sea ice age. This is tracking the ice as it moves around. If you look in the upper left, that's week by week, and going through the months starting in 1985. I'll just let this run as I describe it here. Basically, you see the colors kind of going in and out. That's the seasonal change. That dark gray pulls into the Arctic Ocean in the summertime. It expands out like into the Bering Sea in Alaska, along the coast of Greenland, and then contracts inward. And then the colors indicate the age of the ice, how long the ice has been in the Arctic. So white is older, lighter colors are older, and the white indicates it's been in the Arctic at least 4 years. And the thing that's interesting about this is that the older ice is generally thicker ice. As it ages, it melts during the summer, regrows in the winter, but it tends to grow more in the winter. And so as it ages, the ice gets thicker. So older ice is thicker ice. So the white ice you can think of as the thicker ice that's probably 3 to 4 meters thick, where the darker gray is ice that's 1 to 2 meters thick. And you see the ice moves around with the winds and currents. Now we're into 2000, and you can see the white has been decreasing. It advects out of the Arctic along Fram Strait, but usually in the past we've seen replacement of that, and there'd be roughly an equilibrium. But now what we've been seeing in the recent years is that we're not replacing the ice as fast and the old ice as fast as we used to. And so we're seeing a net loss of the older ice. And as you get into the 2010s here, you can see there's really very little of the oldest ice left, the white bright colors. It rejuvenates every once in a while a little bit, but then it kind of quickly dissipates again. And so there really is very little of this old ice left. It used to comprise close to about a third of the Arctic Ocean was this oldest thick ice. And now it's less than 5% of the ice cover. So it's really a very dramatic change in the ice cover. So not only are we losing the amount of surface area covered, but we're losing the thickness of the ice. And there you can kind of see how it was before. And I'll continue on. So what we're looking at is, the ice is decreasing as the temperatures warm. And so we're heading towards what we consider an ice-free, at least seasonally ice-free Arctic Ocean. And that goes with the temperature, and it's going to depend on the temperature and the emission scenarios that we follow in the future. But right now, global temperatures are about 1.1 degrees C above pre-industrial. And if we're continue on our trajectory, by mid-century, if we get to about 2 degrees, we're going to have ice-free conditions quite normally, at least for part of the summertime, August, September, probably into October. Whereas if we hold things to like the 1.5, like the Paris Agreement, we may avoid, at least by and large, ice-free summers. And this has big impacts. I'll just briefly finish with these. Within the Arctic, of course, there's big impacts. One of them is simply that the Arctic is warming and will continue to warm faster than the global average in the upper left. And that's because the ice, it has a high albedo, meaning it reflects a lot of the solar energy and the sun's energy, the 24 hours of sunlight that occur during the summertime. And as the ice disappears, the ocean absorbs most of that energy. And so, and that allows the ocean to heat up. And so you get this reinforcing, this amplifying effect, where the loss of ice due to warming causes further warming. And there are impacts in terms of local communities within the Arctic. This on the lower left is Shishmaref, Alaska, which is on the coast of Alaska. And that's experiencing coastal erosion due to storms and waves that are happening because it's not protected by the sea ice. Also on the lower right, wildlife is being affected. That's probably a little hard to see there, but those are walrus that are all piled onto a lone ice floe because the ice has retreated so far that they're losing kind of their normal ice platform. And then, of course, there's implications commercially for human activities. Shipping routes are potentially opening up. The Northern Sea Route, which is in kind of the gold color, is already substantially open most years. And other routes are starting to open up more. There's also potential global impacts. These are a little more unsettled. There are some indications that the warming Arctic is causing changes to the jet stream, making it more wavy, more north-south flow, which leads to more extreme weather in places like the United States and Europe. There was the big storm in Texas last year, where there was really cold air, big polar outbursts that got all the way down to the Texas and caused all kinds of issues. There's thought that storms were like that, not that that was necessarily directly impacted by the change in the ice and the Arctic warming, but storms like that are more likely under the loss of ice and Arctic warming. But the science is still unsettled on that, and different analyses are yielding different conclusions. And so we're still waiting, and we still need more data to really determine that. So just to finish up, like I said, we're showing significant trends in the Arctic in all seasons and all regions. The last 15 years have been the 15 lowest Septembers in our 43-year satellite record. And we're heading towards a seasonally ice-free Arctic by probably 2050, if not before, under current projections. And it has wide-ranging impacts within the Arctic and potentially outside of the Arctic. So I'll stop there. Thanks.
All right, thanks, Walt. That's really interesting and pretty scary stuff. So let's move on to Aravind. He works for Tomorrow.io, a weather intelligence company that is working on solving climate security challenges for businesses, governments, and individuals through its platform powered by its weather radar satellite constellation. So Aravind has almost 10 years of experience, including about 6 years in the space industry, working on strategic assignments for space agencies, startups, and investors. Now, he's also the writer and podcaster at TerraWatch Space, aimed at demystifying the developments in the space industry and its applications for Earth. So Aravind, over to you.
Let's get started. So thanks for having me on, and thanks for the introduction there, Sheldon. So yeah, I work for Tomorrow, and I'll quickly give you an overview of the company. I lead the strategy for the space program. So Tomorrow is a weather intelligence and climate security platform that was founded in about 5 years ago, 6 years ago now, that's focused on solving weather intelligence problems for businesses, individuals, and governments around the world. So we've raised over 200 million. We just announced a SPAC transaction to go public, and you can see, all the logos that you have there in terms of who works with us. I'll get to, show the platform in a bit, but our customers range from, the U.S. Air Force to NASA to NOAA, on one end, to enterprises across different verticals in energy and transportation, aviation, etc. And of course, we have, an employee pool that is 50% focused on science and R&D and 50% focused on, day-to-day operations. As I was mentioning before, how is this being done? We are vertically integrated, which means that the platform that our customers use, which contains, I'll get to details of, what are the features of the platform, from weather to air quality to flood risk, and all of that is enabled by deep technology, which is our weather models. I'll get to that again. And of course, soon to be powered by our constellation of satellites with weather radars. Just want to check the chat to see if I have any questions. Going to an overview of how our company works and what we provide. So this slide kind of presents everything that we do for you to understand. So on the left, you see the model. So what is powering the model is all the different data sources that you can think of, starting from our satellites, which will be launched later this year, to public sources of data that we have, data from aircrafts, balloons, ground-based radars. All of that are being ingested into our models. And as a result of that, what we have is a software application, which is a one-stop for getting information on, of course, the weather insights, air quality, flood index, precipitation, lightning information, etc. And then the advantage is that, whatever the workflow is, depending on whoever the customer is, different customers have different kind of use cases, right? Like, for example, for our customers, some of them use our platform as just, a dashboard where they just want to know where to go, when it's good to operate a train from point A to point B, to on the other end, where customers take in our data and integrate it into their internal sources to get weather insights internally. So I mentioned we're vertically integrated. So this is just another version of the slide that I showed you before, but you can see from left to right, from what are the inputs, the models that we created. So Cband is our internal weather model that we created from scratch, and the data layers from precipitation to air quality to flood index, like I mentioned, to how that's being stored, to then finally how the customer uses it, right? So in most cases, as we talk about businesses and how data from different sources are being used for flood, water quality, air quality, what matters is the final last mile delivery, right? Like, that's what we are focused on. So we are, at the end of the day, powered by deep tech, powered by space, powered by all the technologies that are embedded within our models. But then at the end of the day, we are a software company. So that's kind of what our bread and butter is. We are a software company that provides access to weather intelligence on a platform or an API or on a mobile app. So, at the end of the day, we are a vertically integrated software company. Just to give you a quick overview of what a platform looks like. So, you as a customer, they log into the platform, they select their area of interest on a map, and then, they get insights from, when is the best time. So here you can see an example from the trucking and logistics sector where it's, when it's good to kind of, operate a truck from point A to point B. It takes into account everything from air quality to temperature to, weather conditions. So, if there are people working in warehouses, when is the good time for them to take a rest? So, they can just use this dashboard as a one-stop solution for them to have a look at, what to do and where to, when to operate a truck, when to take a break, etc. So this is just one example of how our platform works. Now going to our space. So why do we need to go to space? And why does the software company need to go to space? As some of you might be, aware of, weather is not, it's not the same everywhere when it comes to the access to weather information today around the world. So here you see on the map a list of, or a map of all points around the world where we have radar set up. So clearly, most parts of the world do not have access to radars, and radars, as again, some of the audience might be aware of, is a critical variable when it comes to weather forecasting, to a number of insights within the numerical prediction models. And the only way to close this gap, especially as you see, there's basically none over the oceans, and a lot of weather-related activity, atmospheric activities happens over the oceans, and we need to be monitoring the oceans. So that's kind of the reasoning for us to go to space to collect global precipitation data. Of course, there are missions. There's the NASA GPM mission that's on orbit that provides precipitation data, and it's the only radar out there in space today collecting precipitation data. There was also the NASA RainCube mission that was launched a couple of years ago. That was a demonstration mission for doing that on a smaller satellite. And then of course there are concepts and some planned missions. But what we want to do is to launch a constellation of satellites to collect precipitation data along with other geophysical variables. I'll get to that in a bit, but essentially do that at a fraction of the cost. Have a constellation, which means that your revisit time is going to be every hour, where we're going to have access to data every hour. As a result of that, there's going to be a huge improvement across, from hurricane forecasting to flood risk alerts to a number of activities with respect to, flood and weather around the world. So this is just an overview of what are the geophysical variables we're going to target. Of course, we're going to start from precipitation, going on to other variables. But the point being that it's going to be available every hour. It's going to change the game with respect to global weather forecasting, which is again very much related to everything we're speaking about today, from water quality to air quality. So these are all, that's the foundation of basically everything that's going to come. And of course, I don't have to get into details of how it's going to be useful, whether it's cross industrial, and it has implications in every business, every government, and every individual's lives. That's basically an overview of applications. Who we have a bunch of eminent scientists coming in from JPL to folks who worked in commercial space companies. But yeah, so that's basically an overview of the team. Launch and timeline, like I mentioned, we're launching 2022. Late this year, we'll be launching a couple of demonstration satellites called Pathfinders, and we'll be targeting operational constellation by 2024. Before I finish, just want to highlight one thing that we're doing now is our Earth Science Research Collaborative, which is where we're inviting community, the atmospheric science community, the meteorological community, the remote sensing community to come collaborate with us, because there's going to be a lot of data coming down from our satellites once they get up later this year. But we're already starting work in terms of working together with folks for data simulation, sea ice monitoring to precipitation product creation, and at this stage, a lot of work on calibration and validation and aircraft studies as we go into testing mode. So yeah, so if anybody is interested, please let us know, and you have an email there. You can sign up and let us know if you want to collaborate. Thank you very much.
All right, great. Thanks, Arvind. And again, thanks to all our panelists. A reminder for the audience, if you have questions, please use the Q&A tab, and we'll begin getting through them now. So our first question from the audience is for Oksana, and the question is, there is an increasing number of companies that provide low-cost sensors in the market. Are there any other costs beyond the purchase of the sensor, and for what applications can these sensors be used?
Thank you very much. Excellent question. Indeed, the number of the companies who are providing the low-cost sensors is increasing. And as I said, when you put up the low-cost sensor measuring network, it's not just the cost of the sensor itself. So there is associated cost of the personnel. There is a data infrastructure and the data management, which you have to actually connect to the data produced by the sensors. Sensors have very short lifetime. Some of them just live for 1 year, so you need to plan the refurbishment of the whole observational network already half year after you've installed it. And of course, you need to perform the calibration and validation, which would require you either to bring the sensor to the calibration and validation facility or to bring the reference quality equipment to your facility where you measure with the low-cost sensors. We've done the evaluation of the low-cost sensors, like a network of the low-cost sensors, 100 units. If you implement it somewhere, I don't know, the cost estimate was for US, the 10-year investment would be about 1 million or even higher. So there is a lot of associated cost, which is kind of not obvious when you buy a 10-watt sensor.
Okay, thanks. All right, so Phil, we're going to have a question for you. This comes from Anton. And why did ExxonMobil choose to work with Scepter? And do you have any other large fossil fuel companies lined up as potential customers? 2 parts here as well. Also, do you have any pension funds, fund managers, or life assurance companies as customers? And if so, can you name any of them?
That's a great question. Thanks for asking. I guess the first part, why did ExxonMobil choose to work with us? There's a science aspect to that, and I guess there's an interpersonal aspect. On the science aspect, you know, we have a great science team when you think about methane and methane dispersion and modeling. So remember, our mission is broad. So we're looking at criteria pollutants, methane, CO2, et cetera. But we drilled deep down with ExxonMobil. So part of the equation there was they appreciated that we have a cross-industry approach, and that actually drives a better return. And so we have a better chance at getting to, let's say, the end state and getting our constellation up and operational, which is what our management team has done before. But we were able to tailor down to a 50 to 75 kg methane per hour criteria. So we're not only detecting, we're quantifying and then moving through the other steps. We do have, as a result of the announcement, and since we were able to come out of stealth mode, we have received interest from numerous other operators. And remember, we actually work with industry. So when it comes to methane detection, there's other platforms out there, but I think they're sort of, if you think about the NGOs, I think their modality, as I understand it, is to sort of name where the problem is and shame the person or the entity. We're trying to fix it and not doing the finger pointing. So we believe the industry plus with the influence of ESG, we're trying to support industries to fix their problems. On the pension funds and insurance, I will say that insurance, finance, if you think of some of the big names, we are in discussions, but I'm just not at liberty to mention names, but you can think about all of the use cases with insurance and air quality, for instance, creating new insurance products for the asthmatic population down to the 3-digit zip code based on subpopulation. There's all sorts of ways that the insurance industry could take the information.
Great, thanks. Okay, Irvin, next one is for you. It comes from Chris Little. What is Cband and how does it differ from conventional weather models used for forecasting?
Sure thing. So, well, Cband, the full form is Comprehensive Bespoke Atmospheric Model. So why we decided to do that, it's a good question. It's you know, the simple answer, the short answer is, you know, the need for high spatial and temporal resolution, because, you know, what we have today, you know, it's not at neighborhood level, because when we work with enterprises today, they want to know, if it's a construction company, they want to know if this is the right time to operate a crane. We need to tell them the next 2 hours are, you know, the best time for them to operate their crane or operate their train. So it needs to be available at high spatial and high temporal resolution. That is the biggest reason for us to go ahead and, you know, start developing this. And from an implementation point of view, as you saw from the graphic that I showed, we ingest all types of data into our model. So at the end of the day, it's a model that we are building. We started building it also with our satellites in mind to start ingesting data from our radar satellites as well into our models, so that once that data is ingested, when our satellites are up, our model is ready to kind of leverage on both advances from the public sector, but also what we are building as well. So essentially, the need to do that was to answer to the spatial and temporal resolution that was needed to supply intelligence. If it was on a city level, regional level, it would have sufficed. But then our customers require this on a very, very high resolution. So Cband is a high resolution, high frequency model.
Great, thank you. All right, Walt, we have one for you here. When will the Northwest Passage be open or be a viable shipping lane?
Thanks, Sheldon. Yeah, a good question. So there are several potential shipping lanes through the Arctic. I showed a quick map there that you may have caught. As I mentioned, the Northern Sea Route, which is the route along the coast of Siberia, along the coast of Russia, is already largely open, although it does use icebreaker support. And that's more easily accessible because the ice tends to drift away from the coast. The ice is thinner there, and it tends to open up more easily. The Northwest Passage, which is the more well-known and infamous route, is more troublesome in many respects. The ice is thicker on that side of the Arctic. The channels are narrower and often shallow, and you can actually, even in a sense, as the ice gets less dominant, as the ice extent decreases, it can allow the flow of ice into the channels from the Arctic, which is bringing in more thick ice. So the Northwest Passage, we have seen years where it has opened up, even the kind of wider, deeper channels than what we call the Northern Route, which is really the channels that would allow easy shipping access. We have seen that happen, but it's very unpredictable. The Southern Route, which is the route that Roald Amundsen went through over about 3 years in the early 1900s, that typically does open up a little bit, but it's some very narrow channels to get through, very difficult. So I think the Northern Sea Route is already viable for shipping in large part, but the Northwest Passage is something that's going to be more iffy as we go forward in terms of the future, even as the ice decreases. The Northwest Passage area is going to be one of the last areas of ice. Even during an ice-free summer, we may still have patches of ice there.
Yeah, thanks, Walt. So interesting to kind of think about the famous explorers from the days of yore and how doomed they were, but if they were doing it now, how different the world would be. So yeah, thanks. All right, Oksana, we have another one for you from John Smythe. How would you characterize the current state of public, private, and academic sector cooperation? Great question.
Yeah, this is a great question, and it's actually quite difficult. It depends on the area where we work. There's quite a good cooperation when we talk about the public sector and academia. For example, I work in Science and Innovation Department, and we work very closely with the National Weather Services, but also about 50% of the work which is done by the research community, like research institution, our universities, and so on and so forth. Still, there is a challenge in a number of the countries where we try to engage, even to build this academic and the public sector cooperation, because those have different mandates. For example, the research institutions are not entitled to do any kind of operational or disaster risk reduction warning or the stuff like that. So that's resides with operational community, which is part of the public sector. With the private sector, our WMO started establishing the connection. It's been quite a good collaboration on the sensor side. We have the Association of Meteorological Instruments Producers, which works very closely with the meteorological community and with the public sector. We have joined Expo, where we have the exchange of the ideas. But in general, when it comes to the production of the editorial products, or sharing of the data. As I mentioned in my presentation, there are some challenges because for academia, data is an intellectual property, and though we share them openly, we just ask for the acknowledgement that the data has been used. Though for private sector, it's the source of income. So in many cases, when you ask the private sector to do the open data sharing, well, they earn money with that. And in this case, we need to find the modalities how we can actually benefit both from the cooperation of private and public sector and have those data exchange. Because at the end of the day, we are talking about the saving lives. So we are talking about global goods, even though if somebody puts it as a business case.
Great, thanks, Oksana. Yeah, it's a really fascinating area that we'll be watching over the years for sure. So, Ervin, we have another one for you here. Can you, this comes from Chris Litsky, could you please describe the GPM sensors you're launching compared to current missions, things like frequencies, orbits, etc.?
Sure. So, well, the biggest difference is, in terms of the number of satellites. So, that's related to frequency. So currently, on average, it's going to be 3 days revisit for a GPM, depending on the latitude where you are, between 2 and 5 days, I think. So ours is going to be every hour in terms of our radars. And of course, ours are going to be in low Earth orbit. In terms of frequency, it's going to be in the Cband. We conducted trade-off studies internally, and we work closely with folks at NOAA, NASA, and I don't know if I showed the advisory team and who we are working with. So we conducted trade-off studies, and we ended up with our Cband as our frequency of choice. What else compared to current missions? But yeah, GPM is the only current mission that's that is providing precipitation data, and that's kind of what our biggest differentiation is going to be in terms of the revisit, the higher frequency precipitation data. There are also going to be other geophysical variables. I highlighted that. Precipitation is the one that we're starting with for now.
Okay, thanks very much. Phil, we have one for you here. I think this will be of interest to a lot of young and really entrepreneurial people in the audience. So the areas that everybody's been discussing really seem fertile ground for both new weather data analysis business startups and for would-be investors. Mm-hmm. So based on your history, what advice would you pass on to potential startups and potential investors based on your experience?
Okay, that's sort of broad. Let's see. I guess I would say, when it comes to new markets, and I think if you take a look at ESG and the pressure points that that's creating to understand or have access to data sets that are either atmospheric water quality or land quality data sets, that really it's best to work with an anchor customer when you're going after new markets and collaborate on what your service offering is, and not fall into the I think the traditional trap of build it and they will come when it comes to satellite data. So that's been my experience historically, but we've had the pleasure of again in the energy industry honing our value proposition with Exxonmobil, which is a great lead, and others are following, and we'll do that in other verticals. So try and work with the customers after, when you're going after new markets, and that's not easy. And also space is still hard. It's getting a lot easier, but space is still hard. So, pick your partners there carefully.
Okay, Phil, yeah, great advice. Okay, Walt, over to you. What effect are Arctic sea ice changes currently having on our Atlantic conveyor, Gulf Stream, or I would say really sort of subtropical oceans overall?
Thanks, Sheldon. Yeah, that's a great question. I think the answer is it's still uncertain. The sea ice does play a role, because as sea ice forms, like especially in wintertime, like in the Labrador Sea off the coast of Greenland, it expels salt, which densifies the upper ocean, causes it to sink. And that gets replaced by waters from further south. So that helps drive the conveyor belt, like the Gulf Stream. And so as the ice changes, those areas of that sinking of the ice of the ocean waters is going to change. There's also concern about Greenland and Greenland melt, which is right off the area there where that forms. And Greenland's melting considerably in recent years and increasingly, and that's a freshwater cap. That freshwater kind of stabilizes the upper ocean and prevents overturning. There has been some evidence that the Atlantic meridional conveyor belt circulation is slowing down, but it's still kind of iffy. There was evidence that it was going to happen in like the 2000s, and it kind of was like, no, it was just a little blip. But now again, there's some indication of slowing. I don't think it's anything imminent, but it is a possibility in the future, and sea ice certainly plays a role in that.
Okay, thanks. That's great. Okay, Ervind, we have a question from Alina for you. She says, hi, great presentation, Ervind. What is the fundamental difference between your nowcasting system as it stands now, say before the launch, and state-of-the-art reanalyses put together by major operational climate centers that benefit from a large array of observations from all over the globe, not to speak of the decades of research and operational experience and dedicated resources to data quality assurance before their assimilation into the numerical weather prediction model?
Sure. I think part of this was answered in one of the previous questions in terms of the differences between the models today and why we needed to do it ourselves. I think I briefly touched on this before in terms of the need for temporal and spatial resolution. And well, what I would add is, of course, there's, this is not done, kind of in a silo and as if you're not working. So the folks who work with us come from, who worked at NOAA, who worked, in both civilian and governmental institutions around the world. So it's a question of, learning from each other in terms of what's the best way to build the best weather model, as I mentioned, with the highest temporal and spatial resolution. More importantly, around the world, because it's not, what's available today, it's not the same everywhere around the world in terms of, the access to information in Africa, or, the kind of information, the kind of resolution that we have in parts of, different parts of the world. It's not, the goal is for us to, one of the reasons for, getting to radar and, launching our radars is to improve the precipitation, the observations, which has been acknowledged that, from NOAA to NASA to as one of the, the biggest gaps in terms of weather observations. So that's kind of why we took on that challenge, but also to add on the point of, learning from each other. So, we work closely with NOAA in terms of both from a satellite point of view, but also from the modeling point of view. And in fact, we're working with NOAA for one of their projects called EPIC, the Earth Prediction Innovation Center. So we are, working with NOAA in terms of helping them establish, an implementation architecture internally at NOAA from our learnings of, what we've tried to assemble or what we put together. So, we see learnings on both ends, in fact. So it's not going to be a either or it's not going to be a competition of some sort. It's more of a collaboration, touching on one of the previous questions.
Okay, thank you. All right, Oksana, over to you. Here's, I think, a bit of a follow-on to your previous question. So how can we increase incentives for opening up data? And I think the question is really just kind of like the private sector, right? Now, if not in real time, then with a lag.
Well, thank you very much, Sheldon. Actually, I'm not in private sector, so I would like to address it to my colleagues from private sector. What should happen in the world so that they can actually make access to the to the data that they produce, and if they would be interested in doing so. What we do through WMO is that we started looking at the, let's say, creating the environment where, for example, providing some support to the developing countries where equipment is installed, that the data sharing comes as a necessary condition for continued support. So it's kind of a result-based funding where the support and equipment and training is provided under the condition of the data delivery. And if the data are not delivered, then it's more like a partnership rather than, let's say, a Christmas gift, which is give something and just enjoy, guys, pick on the measurements. So this is how we try to do it with the let's say academic sector and a public sector. Considering the private sector, that's a very good question, and probably we can ask the colleagues on the panel what could make them open their data, considering, as I said, that there are public benefits and public good, in a sense that we can create together are much better systems for the early warning and forecasting working together. Maybe it should be the partnership between, I don't know, the modeling centers and the private sector. We had an example actually. There was a company in the United States that established the network of the Picaro instruments for CO2 and methane measurements. They put up like the 50 devices in the United States and 50 other devices in the all around the world, and they had a particular agreement under non-disclosure. I think they were exchanging the data with one of the producing centers, so the quality of the forecast has substantially increased because the forecasting center was assimilating some additional data. But I think there were some commercial arrangements as well, like the data with data. I don't know the details, but at least I can see that this is possible, and probably it's a subject of discussion so that we can establish this beneficial connection between the private and public sector. I think it's extremely critical.
Yes, I would agree. And I actually would like to just kick it over to first Phil and then Ervin just for any additional comments. And I think the specific part here is coming from the private sector. What do you see as the kinds of incentives that would convince you to sort of open up your data, either in real time, probably not, but maybe with some kind of time lag?
Yeah, first of all, we're supportive of that. We actually, though, obviously have a different financial model. We're actually harnessing the capital markets and have to drive a return for investors. Whereas I think in the government missions, the money's coming from taxpayers, but there's no guarantee on continuity of the mission. You can take a look at the whipsaw here in the US with administrations, and there's just no guarantee that there'll be a re-up on something that's working really well. So I think, and then we all have our personal interests, right? I'm personally motivated to, I'm doing this not only for a return, but for all the good that I think everybody would cite on this panel. So I think the answer, obviously, Sheldon, resides where you're pointing to, which is, it's some type of temporal aspect. Maybe it's a delay on the data and that becomes free, or it could be some type of group purchase where we can then provide it for better means. But we're considering all aspects.
Okay, thanks, Phil. Yeah, Ervin, anything you'd like to add to that, or does that cover it more or less?
Yeah, what I'd add is, it's a subject, of course, we've thought about a lot internally, and we've had a lot of conversations with the WMO, with NOAA, with NASA, and with many agencies around the world, and of course from our advisors as well, who have experience in in all these institutions. So I think there are two things that I want to point out. One is on the need to kind of transfer the value of the innovation. It's transferred, I think, the last mile delivery, again, like I mentioned, what tomorrow is focused on is the last mile delivery. And, that is kind of what we want to focus on and want to push, because there is, that's on the long term, that is something we need to figure out with the WMO in terms of, incentivizing the private sector to kind of do that. And those conversations are ongoing, like I mentioned, with the WMO and NOAA and all the meta agencies. But on the short term, what we do want to do is to, transfer the value of the innovation. That's why we created a nonprofit arm. It's called Tomorrow Now. And we're working on a couple of projects. One from, we just got a grant from the Gates Foundation to, provide these last mile services to farmers in Africa, because, the long-term vision is to have the data supply business model figured out and then for Met agencies around the world to have the capacity to ingest this data, whatever we're going to provide, and other sources of data, internally, to then have that figured out. So in the short term, we still want to focus on the last mile delivery, and that's kind of where I think there is a big gap. And we also have visions of what would be the best way to solve this once and for all, especially from a weather point of view. But then it's going to be a longer discussion. So I'll stop there in terms of how we're thinking about it.
Great, thanks. Okay, excellent question. All right, Phil, we're going to go back to you. Specific to Scepter, how are you different from the NGOs of the world that are out there, your methane sats, your carbon mappers, who are also pursuing methane leak detection via satellite?
Okay, well, on that vertical, and again, our mission is broader than just methane, but on the energy vertical, we've crafted an information service offering with Exxonmobil that not only detects, quantifies, but it informs. We move into an abatement phase and then certification phase. So we've constructed with our platform the ability for the operator to conduct its business and work side by side with the regulatory agencies. So we've gone much deeper than I think you would find with the NGO missions, which are at least heretofore constructed for just detection. Hey, there's a big leak over there. Somebody's responsible for it. We're going to make it visible and let the broader community know. And that's a viable business model as well. Or I shouldn't say a business model. That's a viable approach to trying to help the situation that we all find ourselves in. But we're working closely with industry, and we're more aligned with ESG principles, and believe that industry can take care of itself over time and move in the right direction.
Okay, thanks. Okay, Walt, back to you for a question. Do you think it's possible for the Arctic, and let's also add the Antarctic here, sea ice to recover?
Thanks. Yeah, great question. And that's one. I think this is a piece of good news. As we talked about, it's a little bit depressing to see the Arctic declining, and the Arctic and the sea ice is a pretty sensitive climate indicator. Like I said, even at its thickest, it's generally maybe 3 or 4 meters thick, other than when it piles up into thick ridges. And so it melts away pretty easily and responds quickly to the warming temperatures. And there's this amplifying feedback. But that means it works in reverse too. So if emissions decrease, if the temperatures come down, the ice can recover pretty quickly. We see this from year to year. You see up and down years depending on the weather during a given season and a given year. So within a few years, we could get the ice cover back, at least the surface area covered. It would take a while to thicken up again. But it is a kind of a hopeful aspect that we do control how the sea ice will go, and it can potentially recover quite quickly.
Okay, that's promising to hear. All right, Erwin, to you next is a bit of a saucy question, to be honest. So to what extent can private sector services substitute for those of a national Met service, and where would they fall short? Yeah, good luck.
It's an age-old question, isn't it? But I think I alluded to this before. It's not going to be an either or. It's probably going to be a combination. I can point out to several examples where we used as a primary source of weather information. I can think of enterprises that we work with, from aviation companies to companies in take the US Open or the NFL, for example. They're our customers, and they're just okay if the private sector, all they need is an alert to know, looking at the dashboard, pause the game between 4 and 4:30 p.m. because there's going to be a heavy gust of wind if it's a US Open. That's what they need to know, right? Like, they wouldn't even need to know where this information comes from. So for those, I think the private sector can be, even though we are dependent on data, we're just not going to use only our data, right? It's going to be a combination of different types of data coming in from different parts of the world, from different agencies. So for those audience, maybe the private sector, in terms of the last mile delivery, like I mentioned, in terms of giving them the information in the way they want, at the right time, the right place, in the right format, that could be more interesting. But then even when it comes to governments, we've been engaging with a lot of governments, and we work with plenty of cities now, especially given the time we're living in, and some of them use Tomorrow on our platform for second opinion, which is also fair, because they already have their primary source and they just want to go get a second opinion. And there are governments and cities, state and local, that we work with. They are looking at it as primary, but it depends on a case by case basis. I don't think there's always it's going to be a either or, like I mentioned. So yeah, it's going to be a combination. The combination, how is it going to look like, is something that we're going to figure out over the next few years, as we launch our satellites and continue to improve our models to work around the world, and also engage with governments and med agencies around the world, because right now some of them are as not as as kind of in terms of having capacity compared to what we have in the West. So in terms of how they want support could also be different. Maybe some of them are require minimal kind of collaboration. Some of them require very, very high collaboration with the private sector. Anyway, I kind of hope I kept it diplomatic.
Yeah, no, yeah, beautiful answer. And I think it's a really interesting part of the market space that's going to develop over the next 3, 4, 5, 10 years, et cetera. So thank you. All right, Oksana, over to you. Here's another, I think, really interesting kind of related question. How can the user assess the quality of the data and the forecast that he or she is getting via open source platforms or commercial data? And maybe who is responsible for data quality here? And are there any legal responsibilities for the provision of wrong data?
Let me start from the end. That will probably answer the beginning. To the best of my knowledge, there is no responsibility for the provision of wrong data. So you can go in internet and you can grab an internet from different sources, whatever it is. And we've seen this happening with people, establish the low-cost sensor network and start pushing it in the internet without actually even checking what it pushes into internet. We've seen sometimes that some organizations just produce a very nice, colorful plots. I mean, the design is amazing. I mean, how you can do from the poor data a beautiful design. This is a piece of art, but there is no big science behind. We've been evaluated a number of such products with our scientific community, and there was quite a lot of criticism about how the data we use. There is just like a big data science when the crunch of the satellite data just happens and the calibration is done versus low-cost sensors. You multiply one unknown with the other unknown and just build a beautiful map. Unfortunately, unlike in the weather community, there is no scoring for the chemical transport models. It is just not there. We are developing the methodologies, and probably we will set up the benchmarking exercise where everybody can run a particular scenario, a particular set of data to just quantify the uncertainty in the model or in the forecasting system and put the score. So the user community, when they go on internet and download different products, they can be completely confused. So our advice is to use the authoritative sources, like if it is a respected university, or if it is the regional or meteorological center, or if it is a global center like ECMWF or Cooperative, when you would be sure that the quality of the products and services which is provided by those institutions is really reliable, rather than just looking at some unknown institutions who produce something. And as I said, it's very difficult. The user community is completely confused, because even within research community, we produce a lot of products, and we are not for sand and dust. You've seen there are 12 models which are participating in multi-model forecast, and we take the average because none of the models is perfect. They have the uncertainties. And if you are just a private company with a one engineer, one computer scientist, you cannot do multi-model, right? You just have one. How good it is? Well, that's a good question. Do you participate in inter-comparison with international institutions? Probably not, because you are not part of those consortia and a scientific community. So we need to be frank, and we need to do much better job with that.
Okay, great. Thank you, Oksana. Okay, Walt, here's an interesting one for you that really hits home one of our real problems of the day. So, Walt, can you say anything about the impact of atmospheric and seaborne plastic pollution in changing the sea ice cover? Are we finding plastics in the sea ice itself? Do we know anything about that?
Yeah, great question. It's definitely outside of my area of research and my familiarity, but I did recently just come across a paper, a report on this, and yeah, they are finding microplastics within the Arctic and within the ice and snow in the Arctic. You know, it goes in the ocean transports things, and so yeah, it's a concern because you know the cold weather and the potential on wildlife. And so, yeah, like I said, I don't know a lot of details, but I've seen reports of that. I think Oksana raised her hand, might have a comment to contribute to that too. So go ahead.
Okay, perfect.
Yeah, I just wanted to comment in here. There is a group of experts on marine aspects of environment called GISOM, and under GISOM there is a one specific working group a working group body which works on marine microplastic, and indeed there's a lot of different sizes of plastic in the ocean dissolved, and there is a resuspension of the plastic in the atmosphere. The fluxes are largely unknown. So we had a workshop last year where we spoke between the working group 38, which works on the supply of nutrients to the ocean, with this plastic working group, and there is a paper in preparation which goes in Nature that gives a perspective on the whole area of the plastic cycle and exchange of the plastic between the atmosphere and the ocean. So stay tuned, it should be in publication quite soon.
Great ad. Thanks, Oksana. Okay, well, that concludes this webinar, which has again been organized by InterMET.digital. I'd just like to thank all of our panelists and everybody in the audience for taking time today to join us. And I hope we've all gained some useful insights into air and water quality and plastics in the ocean, right, in the context of climate change. If you have any further questions, I would ask you to please contact our producer, Ian Harper, and his details will be provided shortly on our outro. Also, a recording of this webinar will be available in the near future and will notify all those who registered for today's event. So to conclude today's webinar, it's goodbye from me, Sheldon, and from our panelists, Oksana, Phil, Arvind, and Walt. So to play us out, we've prepared a short video with our contact information. Goodbye for now and stay safe.